Now we come to the last lecture of this discussion on the MOSFET characteristics. This lecture will also be the penultimate lecture of the course. So we will have one more lecture which will summarize all that we have done in this course after we discuss a few advanced devices at the qualitative level. Coming back to the discussion on the MOSFETs, let us summarize what we achieved in the last class. In the last class we have written these equations which are in accordance with what is called the square law model. In these equations the current rises as a square law function of the drain source voltage for drain source voltage less than VGS minus VTS. This VGS minus VTS is the so called saturation drain source voltage. So once the transistor is in saturation, according to the square law model, the current is constant at this value, which is obtained by substituting VD sat for these two VDS terms, and these are the expressions for the threshold voltage and the body effect parameter which enters into the threshold voltage. Now this threshold voltage is with respect to the source. Please recall that in the MOS capacitor discussion and also in the early stages of derivation of the MOSFET characteristics, we have always considered all voltages with respect to bulk, and therefore the threshold voltage expression was with respect to the bulk. Whereas in practice when you use a MOSFET, the source is normally the common terminal, and therefore here in these equations we are using all the terms with respect to the source. This equation also includes the body effect, as you can see from the VBS term coming here. Now let us proceed further with the square law model and see what other effects we need to incorporate. The graph of the square law model is drawn here. This is ID versus VDS. This dotted line shows the separation between the linear and saturation regions. So this is the linear region. It is also called the ohmic region, and this is the saturation region. Now please note that though we call this linear, strictly speaking only in a very small range near origin the characteristics are linear. This dotted line here shows the current in saturation. It is a flat line, right, constant, independent of VDS, something that does not happen in practice. Now what is the equation for this particular line which separates the linear and saturation regions? This can be readily obtained from the saturation current voltage characteristics, that is this particular characteristics. If you call this as the current ID sat and call this as the voltage VD sat, then we have ID sat equal to this term multiplied by VD sat square. Now that is what is the shape of this particular dotted line here. So this dotted line is following the law ID sat is equal to some constant which is mu n C naught W by 2L into VD sat square. So this is the saturation voltage and this is the saturation current for this curve. You similarly have saturation current and saturation voltage for the other curve. So this equation represents the locus of the saturation points as a function of VGS and VDS. Now how do we treat this region here where the current rises slowly? okay, because of channel length modulation. So the channel length modulation effect we have already explained qualitatively using a diagram. We will redraw that diagram considering a real MOSFET, that is, this is your drain and this is your source, and then you have the gate here, this is the oxide, this is the p-type substrate. Now if you show the depletion region and the inversion charge, it will look as follows. We are showing beyond saturation. So beyond saturation, the picture is something like this. This is the inversion charge decreasing from source to drain and becoming 0 here, and then you have the depletion layer coming like this. The depletion layer is smaller at the source because drain to bulk voltage is more than source to bulk voltage. Of course, in our characteristics we have assumed the the source to be shorted to the bulk. So therefore both the source and bulk are ground, and here you have the voltage VGS, and here you have the voltage VDS. Now this shift of this point from this end is the channel length modulation, delta L. Now this delta L is responsible for the increase in current, because this delta L goes on increasing with this VDS. This increase in delta L with VDS can be approximated by a square root formula of the following form. Delta L is proportional to square root of the difference between VDS and VDSat, because you know that when VDS is equal to VDSat, delta L is 0. So this point will coincide with this point here when VDS is equal to VDSat at saturation. Now beyond saturation the point is shifting. So we are showing these conditions for VD greater than VDS greater than VDSat. Now how do you get this square root dependence of delta L? Well, you can do a detailed derivation which is beyond the scope of this particular course. All that we need to remember here is that when you take a p-n junction and you try to express the depletion region of a p-n junction in terms of the reverse bias, you find that the depletion width varies as square root of the reverse bias. Now that is essentially what is being used here. So delta L is this distance over which the electric field falls, and this is a depletion layer. So width of this delta L depletion width is a function of the reverse bias that is causing this depletion width. Now the reverse bias that is responsible for this width is VDS minus VDSat. Now note that the reverse bias that is responsible for this depletion width here is VDS. Okay, it is VDB, but since B and S are connected together because VBS is 0, therefore VDS is the voltage drop here. So VDS is responsible for this width, but VDS minus VDSat is responsible for this width. So that is the kind of expression you have. Now how does this delta L affect our equations? Let us incorporate delta L and then we will have the equations as follows. In this particular equation which is valid for saturation, we should replace L by L minus delta L. This delta L does not come into picture for this equation which is below saturation. So we can now take this L out of this particular bracket, in which case the equation will get modified to L into 1 by 1 minus delta L by L. Now since this delta L by L is generally small, much less than 1, therefore 1 minus a small term much less than 1 can be approximated as simply 1 plus that term. So we use the approximation 1 minus delta L by L, the reciprocal, is approximately equal to 1 plus delta L by L, since delta L by L is much less than 1. So if you do that, then this will go in the numerator. Okay. So that is your equation including the channel length modulation. Now since delta L increases with VDS, this particular equation shows a small increase with VDS. Now let us plot this effect on the graph. So if you draw it on the graph, then what is happening is that you have a curve that is slowly increasing like this. Now one problem here is that while the slope of this curve is non-zero and positive, it goes like this, the slope of this particular segment according to the square law model at saturation point, this slope is 0. So you have a discontinuity in the slope here. Now how do you take care of the discontinuity in the slope? Because this discontinuity is not good in modeling calculations. A discontinuity in the slope creates problems when you use this model for computer calculations. So you can avoid the discontinuity by using the following trick. So what we do is, this delta L by L, when we want to represent in terms of the drain to source voltage, we use a simple empirical approximation to the square root formula. So look at the square root formula, delta L is proportional to square root VDS minus VDSat. So delta L by L will also be proportional to the same quantity, but we write delta L by L as proportional to simply VDS, and we include a proportionality constant that is normally represented as lambda, and this proportionality constant is called channel length modulation parameter. Channel length modulation parameter. Now after doing this, what we do is we include that lambda VDS term also in the expression below saturation. That is, here when you include the expression lambda VDS for delta L by L, you will get, this will get changed to 1 plus lambda VDS. and then what we do is we use this term, multiplying term, also here. So this also we multiply with 1 plus lambda VDS. Now please note, this is not physical, because the channeling modulation does not take place for VDS less than VGS minus VTS, but still for mathematical continuity of the derivative and the equation, that the value of these functions, because these are two different segments, we must ensure that the segments are continuous at the point where they meet. So there should be continuity in the value of the two segments at that point, and there should be continuity in the value of the derivative also. So that is why this is done. Now please note that since this lambda VDS is really very small compared to 1, it does not affect this current significantly, okay, but it provides that small increase in current in saturation required here. So when you make these changes, if you look at the graph will now look continuous, it will be something like this. So instead of this current, your current will be slightly more, very slightly more, but here the slope will not be 0, it will have this slope that you require for the channeling modulation effect. That is the difference, okay. So we can remove this to avoid complication. And that is the kind of curve you get, a smooth curve. Now here also you will get a similar curve, except that the slope of this curve is less than the slope of this. Now that point is very clear from the mathematical equations. If you look at these equations here, let us say you write this equation, okay, simply as follows: IDS is equal to ID sat into 1 plus lambda VDS, okay. This is the equation for this segment here. So from here it is clear that dIDS by dVDS is equal to ID sat into lambda. Since lambda is a constant, but ID sat increases with VGS, therefore the slope dIDS by dVDS, which is the slope of this line, increases with VGS. In fact, it increases proportional to this current ID sat, and as a result, if you extend all these lines back like this, you will find that these lines will tend to meet this particular voltage axis at a common point. Now this can be shown nicely if you compress the graph. So if you compress the graph, let us draw it here. So if you compress the graph, it will look like this. And then you separate the linear and saturation regions, and then you complete this curves. Now this is very much like what we have done for the bipolar junction transistor. Even there, if you recall, we said that the way to draw the complete curve is to first separate the linear and saturation regions, that is active and these regions, using this line. Then you draw the curves in the active region starting from a single point, then you identify the saturation points, and from there you connect up the origin. So this is the way to draw the current voltage characteristics including all effects. Now just one point, let us look at the square law equation here, ignoring this fine adjustment that we have made for achieving model continuity. Let us just look at this equation. If you use the same equation beyond VDS equal to VGS minus VTS, what is going to happen? If you draw the square law equation beyond this saturation point, that is, this is VD sat and this is ID sat. So beyond the saturation point, if you draw this equation, you will find that this equation will come down. It will be like a parabola shape. It will come down, and here the current will decrease with voltage, showing negative differential resistance, because current decreasing with voltage means the slope of the ID/VD curve is negative, which means the resistance is negative. Now obviously this is not physical, that is why we do not use the square law segment beyond this point. Now physically, the reason why square law segment is not used we have already explained, beyond the saturation point. The reason for that is the square law characteristic is derived assuming that the inversion charge is present over the entire channel length from source to drain. But once saturation is reached, the inversion charge becomes 0 at the drain, and therefore beyond that point you cannot use that equation. Now let us look at the experimental characteristics which we had shown at the beginning of the discussion on the MOSFETs. Let us see what are the various features that we have explained of these characteristics. So these characteristics are shown on the slide. So we have explained the linear region here, then the saturation region here, and variation of the current as a function of VGS. So this is that line ID sat proportional to VD sat square. Now one thing you find here is that the spacing between the various current lines in the saturation region for different values of VGS does not seem to follow a square law, because if the segments in the saturation were following a square law, and if the steps in the gate source voltage were constant, okay, if the gate source voltage was increasing in equal steps, as you can see in the slide. So here you find that the gate source voltage is increased in steps of 1 volt. So if the gate source voltage was increasing in such equal steps, then a square law means that the spacing between the currents should go on increasing, because the ID sat is proportional to square of the VD sat. In other words, it should be proportional to square of VGS minus VT. So that means a square law means the following kind of spacing. So suppose this is the ID sat for one gate source voltage, and then you make an increment in the gate source voltage and you get another ID sat. Then if you make an equal increment in gate source voltage, your current should be much above here, right? So this spacing between the saturation currents should be more than this spacing. In fact, let us exaggerate this a little bit. to show this clearly. So this is equal spacing in gate source voltage, that is VGS. If this is VGS, this is VGS plus some delta VGS, this is VGS plus 2 delta VGS. So this spacing should go on increasing. So in fact the next spacing will be even higher and the spacing here would be lower, something like this. So this is VGS minus delta VGS. Of course we are assuming that this quantity is more than VT, all these are more than the threshold voltage. So this is what we should have as per the square law curve, square law behavior. But what we find on the slide is that the current, the spacing between the currents doesn't seem to be increasing that much as you start from low values, and in fact in this region it appears to be almost kind of same. Now the reason for this is the mobility degradation. So what is happening is, here in this equation we are assuming the mobility to be constant, okay. So the same here, or you can take this equation which is the equation in saturation. So we are assuming this mobility to be constant in this equation with gate to source voltage, but as gate to source voltage increases actually the mobility falls. That is why if you replace this mobility by the average mobility that we have putting here, you replace this constant mobility by the real mobility which varies with gate to source voltage, then you will get a term dependent on gate to source voltage in a denominator that will cancel to some effect the effect of this square term, and it will become almost linear in VGS minus VT. So it is the mobility degradation with gate source voltage, and of course mobility also degrades with drain source voltage. So this mobility degradation is responsible for the deviation from the simple square law behavior of the saturation current versus voltage characteristics. Now these characteristics here are not showing the breakdown precisely, but you can see that the current has started rising here in these regions. So basically they are approaching breakdown. The breakdown in the case of MOSFETs is not as complicated as in the case of bipolar transistors. In bipolar transistors you had two types of breakdown voltages, namely the BV-CEO, that is breakdown voltage between collector and emitter, and breakdown voltage between collector and base, BV-CB. Whereas here you do not have any such different breakdown voltages, because very simply the breakdown occurs when this particular drain to bulk junction breaks down, okay. So the breakdown phenomenon in MOSFETs is very simple. So all the characteristics when they reach breakdown, they will simply go up like this at the breakdown point. Now that completes the discussion of the DC characteristics. Now just one point I would like to emphasize, all the discussion of our DC characteristics that we have done, the physics, the equations and so on, we have developed assuming a surface channel MOSFET, okay. So here this charge that is carrying the current is because of inversion layer. Now this kind of analysis also works for buried channel MOSFETs in an approximate manner, but otherwise in a buried channel MOSFET wherein the channel is because of a doped layer here in this region, in such cases, particularly when the doping depth is deep, or the thickness of the channel from the interface is more, the theory is a little more involved and the equations are little more complicated. This point should be borne in mind. However, whatever we have derived assuming a surface channel MOSFET is approximately valid for different types of MOSFETs that we have discussed. Another point about the symbol of this MOSFET. So far we have been using a 4-terminal MOSFET symbol. For example, look at this slide. So here we have been using a 4-terminal MOSFET symbol because the MOSFET really has 4 terminals: the drain, the source, the gate and the bulk. But as shown in the slide, in many applications the bulk and the source are connected together. So in order to avoid complications in drawing a circuit consisting of a large number of MOSFETs, if for all the MOSFETs the bulk has been connected to the source, it is useful to use a simpler symbol. That simpler symbol is a 3-terminal symbol as follows. So this is the 3-terminal MOSFET symbol. Where the bulk has not been shown, it is assumed that bulk to source voltage is 0 whenever you use a 3-terminal symbol. Now how do you distinguish between a normally on and normally off device? This is a normally off device. If you want to show a normally on device, all that is done is this line is made thick. So here you have gate, drain and source. Now let us discuss the small signal equivalent circuit of the MOSFET. Now in this slide one can see the various elements shown. This particular equivalent circuit is very much like the hybrid pi equivalent circuit of the bipolar junction transistor. In fact, it is somewhat simpler because some components are not there. So let us develop this equivalent circuit starting from the device equations and physics. Now this equivalent circuit is shown for bulk to source voltage equal to 0. So please look at the equivalent circuit again. You will find that the bulk terminal is not shown at all. So you have only 3 terminals: gate, drain and source, and here you find a suffix dB, that is drain to bulk, and this point has been connected to source. So this point also emphasizes that the bulk and source have been assumed to be shorted. Now let us develop this equivalent circuit. So the biasing arrangement here is as follows. So you have a DC voltage applied, gate source voltage, and then you have a drain source voltage. You are superimposing on the gate source voltage a small signal, an increment, and you are trying to find out what is the effect of this increment here. So as a result of the increment, you are getting an increment in ID. Fortunately, in a MOSFET there is no DC current at the input. So whatever current input you see here because of the increment is only because of capacitance. So if the increment is at very low frequency, in fact you will not see any input current here. So we need not bother about this part. So we have to relate this delta ID to delta VGS. Similarly, if you make an increment in VDS, then also there will be an increment in delta ID. So the increment in delta ID is because of increment in delta VGS and also because of any increment in delta VDS. So by using this kind of an approach, you can identify the roles of various
and how the components are related to physical phenomena. For example,
the change in VDS introduces a change in ID because of channel length modulation. So if you look at the characteristics in saturation, so this is a saturation point, change in ID because of a change in VDS, that is the slope here. Now another point to note is that the equivalent circuit is normally shown for the device working in the active region. So the bipolar junction transistor equivalent circuit was also applicable in the active region. So here in the MOSFET also this must be, this condition is always, this condition always holds. Okay. So the small signal equivalent circuit is shown or is used in the active region when the device works as an amplifier. Now change in ID because of a change in VGS gives rise to a transconductance. That is why between drain and source you have a transconductance. So this is GM, and if you show the increment using a lowercase letter, small VGS is the increment. So here you have the gate and source terminals. So you are making an increment in the gate source voltage, and the result is a change in the drain current. So that change in the drain current because of change in the VGS is shown by a transconductance amplifier. Now the change in current ID because of a change in VDS is shown by a resistance. So this resistance is RDS, or very often this S is dropped and you simply call it RD. So that completes in fact a part of the circuit which is applicable at low frequencies. So without the capacitances, this is the circuit. Now we must add the capacitances to this circuit so that it can be used at high frequencies. Now what are the capacitances? To understand the capacitances, let us look at this device structure with the various charges. So if you look at this device structure, you find that there is an overlap between the gate and the drain here, and similarly there is an overlap between the gate and the source here. Okay. So if I expand this, this is the source and this is the drain. So this is the so called overlap region. So you have a capacitance between the gate and drain because of this. Okay. So this capacitance, and similarly you also have a capacitance between the gate and source. This is source and this is drain because of overlap. Now what about the capacitance between the gate and this channel charge? So this capacitance between gate and the channel charge is normally separated into gate and drain and gate and source. Now this apportioning of this capacitance because of channel charge between drain and source is a function of the gate source voltage. Now this apportioning formula for this is beyond the scope of our first level course. So we will just remember that this capacitance between the gate and this charge, okay, this capacitance is separated between gate drain and gate source capacitance. So therefore you have only C drain, so C gate drain, and this is C gate source. In addition, you have a capacitance between drain and bulk because of the junction. This is a PN junction, and here you have this depletion layer. So there is a capacitance associated with this. So this capacitance is actually CdB, C drain to bulk capacitance. Now since this bulk and this source, there is a common terminal here because these are shorted, therefore this CdB is also appearing as CdS. So now if you put these capacitances in our equivalent circuit, they will appear as follows. So you have CGS here, you also have CGD here, and you have drain to bulk, which appears as drain to source. So you have a capacitance here, CDB or CDS. So that completes the equivalent circuit. Okay. Now you look at your slide, all the components and their origin has been identified. So this is the resistance RD, which represents channel length modulation. This current source represents the transconductance, which contributes to the small signal amplification. And then for high frequency purposes, you introduce these capacitances which are related to the device structure. Now, what are the typical values of the components? Now these values depend on the bias conditions, namely the drain source voltage, the drain current and so on, as in the case of bipolar transistor. Now I will give you some values for some particular bias currents in a MOSFET. So bias currents are of the order of milliamperes. Okay. The value of CGS is 4pf. Please understand this is only an order. CGD is 1.1 pf. C drain bulk is about 1.6 pf, and RD is about 200 kilo ohms. So this RD is generally more than the corresponding resistance in the case of bipolar junction transistor. As far as the value of GM is concerned, we will do a solved example to see what this value is like. Now this is the example. Calculate the current and transconductance of an N-channel MOSFET having the following physical parameters: channel length 5 micron, channel width W 100 micron, oxide thickness T0 500 angstroms, the average channel mobility of electrons mu n bar 300 centimeter square per volt second, threshold voltage Vt is 1 volt, and bias voltages are Vgs equal to 4 volts, Vds equal to 6 volts, and Vbs is 0 volt. The threshold voltage is given for Vbs equal to 0. What is the value of the channel length modulation parameter lambda for this device if Rd is equal to 200 kilo ohm at the given bias conditions? Now let us look at the structure of the device. This is the top view and this is the cross section. The oxide thickness is 500 angstroms. The channel length is 5 micron. So this is the distance between the source and drain junctions. Now for the sake of completion, some typical values of other geometrical parameters are also shown in the MOSFET. This will give an idea of the typical MOSFET geometry. So you find that the depth of this source and drain regions is about 0.3 micron. This is a rough order. The overlap here is related to the junction depth. It is about 60% of this junction depth, 60 to 70%. So this is about 0.2 microns overlap. So here also you have 0.2 micron. So the width of this gate here is more than the actual gate length, which is 5 micron. Then on the top view you can see this is the width 100 microns, and the width of this source and drain regions here, this is about 5 micron. So this diagram is not to scale because 100 micron is 20 times 5 micron. So it is really long in this direction. That is why we have shown a cut. The thickness of the wafer is 100 to 150 microns. Now let us see what are the various equations that we need to use. For this purpose, let us look at the bias conditions. This is the circuit. Since VBS is equal to 0, we are using a 3-terminal MOSFET. Now VGS minus VTS is 4 minus 1, that is 3 volts. So this 3 volts is less than VDS, which is 6 volts. So therefore the device is in saturation. So since the device is in saturation, we must use this equation here for the current. Now what about the expression for transconductance? The transconductance expression is derived by differentiating this expression with respect to VGS. So you see here Gm is dID by dVDS. This is wrong, it is dVGS. So when you differentiate this square law expression, you will get 2 here and you will get a linear term in VGS minus VTS. So that is what is shown here. Now we can write this in a more compact form as follows. You multiply and divide by VGS minus VTS, and then you divide by 2 here and you divide by 2 here. After this you can recognize that this whole term is nothing but ID. So in a very simple way we can write this Gm as ID upon VGS minus VTS divided by 2. So current by voltage. Okay, this is very easy to remember. Now let us see what is the expression for lambda. Okay. Now the expression for lambda is obtained as follows. You know that RD is 1 by dID by dVDS. If you differentiate this expression in saturation with respect to VDS, you will get a lambda here and you will have this quantity which we represent as ID sat. Just this quantity without the 1 plus lambda VDS is ID sat. Therefore this quantity is 1 by lambda ID sat, and therefore you can transform this and you get lambda is equal to 1 by RD into ID sat. Now we can calculate the numerical values. So first we calculate ID sat. This is mu n bar 300 centimeter square per volt second. This is C naught 71 nanofarads. So this farad per centimeter square, 10 power minus 9 here for nanofarads. Then this is W by L. This is VGS minus VT square, that is 3 square. So 3 volt square by 2. Now you can see the units. 1 volt cancels here. Farad into volt is coulomb. Coulomb by second is ampere. So the unit here is ampere. So if you complete the calculation, you will get this as about 1.9 milliamperes. Now we can substitute this 1.9 milliamperes here to find out lambda. So lambda is here 200 kilo ohms into ID sat is 1.9 milliamperes. So obviously the unit is kilo ohm into milliamperes is 1 by volt. So this result is 1 by 380, which will be about 2.6 into 10 power minus 3 per volt. Okay, so this is your lambda. Now finally we can evaluate the GM. To evaluate the GM, we have to find out ID. This ID is ID sat into 1 plus lambda VDS, as you can see from here. This is ID sat into 1 plus lambda VDS. Now actually this lambda VDS term is going to be rather small, so we can neglect it. We can in fact assume that this is approximately ID sat itself, and so your result will be 1.9 milliampere by, this is 3 by 2, that is 1.5 volt. So this is approximately 1.27 milliampere per volt. So that is the kind of GM you have. These are the typical values of the various parameters. So with that we complete the solved example. Now as a final topic, we will compare the MOSFET along with the BJT. What are the differences in the operation of these two devices? Now here is a table which shows the differences. We have listed the various aspects of the two devices that we are comparing in this column. Let us take the first, the structure of the device. The BJT is unilateral device, whereas the MOSFET is bilateral. Let us see what we mean by this. This is an NPN BJT and this is an N-channel MOSFET. Both these carry current due to electrons. You can see that the emitter is very heavily doped compared to collector, so you cannot interchange collector and emitter. Whereas in the MOSFET, you can interchange the source and drain because these are identical. So current can flow either this way or the other way. This has great advantages. The MOSFET can be used as a bilateral switch in many applications. The next thing to see is the current flow. In BJT, the current flows because of excess minority carriers, whereas in the MOSFET, the current flows because of majority carriers. Now students sometimes have a doubt that the inversion layer of electrons is actually made of minority carriers as far as the substrate is concerned. Now please note that in the inversion layer, the concentration of the carriers, let us take a p-type substrate, concentration of electrons in the inversion layer is more than that of holes. So in the inversion layer, electrons are majority carriers, okay, though they may be minority carriers as far as the bulk substrate is concerned. So this is important to understand. Now the current flows by diffusion in BJT, whereas it flows by drift. We will see some advantages of this in the case of MOSFET. Let us see the small signal parameters next. The most important parameter is the GM, which tells you how much gain you can get. The BJT, the GM is IC by VT, whereas in the MOSFET it is ID by VGS minus VTS by 2. That is half of this difference between VGS and VTS. So if you compare the GMs for the same collector and drain currents, the GM of the BJT will be very high because this VT is 0.026 volts, whereas this term half of VGS minus VTS is of the order of volts. Another property related to this GM is that this term here for the MOSFET depends on the geometry of the device. Threshold voltage depends on the geometry. Therefore, the value VGS minus VTS for any ID depends on the geometry. So the GM is geometry dependent in the MOSFET, whereas in the BJT this VT is independent of any geometry, a great advantage, and therefore it is geometry independent in the case of BJT. So high GM and geometry independent of the structure, great advantage for the BJT. Let us look at the input impedance of the BJT. Now there are two possibilities. You have the common base or the common emitter mode, right? Let us compare these two. You also have common collector, but even there the input impedance is same as common emitter. So here you find in a common emitter the input impedance is beta plus 1 times Re, which is of the order of kilo ohms, because Re is of the order of tens of ohms. In a common base it is Re, of the order of tens of ohms. Now, so these resistances are not very high. It is because you are seeing a forward biased diode in a BJT when it is used as an amplifier, whereas in a MOSFET the input impedance is very, very high because there is an insulator between the gate and the channel. Now, let's look at the current gain. In the case of BJT, the current gain from base to collector is 50 to 150, whereas it is very high in the case of MOSFET because there is really no input current into the gate. Finally, the breakdown. In BJT, you have at least two different breakdowns, BVCEO and BVCBO. So this breakdown is much less than the other breakdown. Breakdown between collector and emitter is much less than the breakdown between collector and base. Now, in the case of MOSFET, however, there is no such problem. Okay? So breakdown voltage between drain and source is the same as breakdown voltage between drain and bulk. A very important thing that we should consider related to breakdown is the mechanism of second breakdown which afflicts the BJT. Let us understand this mechanism with reference to the diagram here, which shows a parallel combination of devices. This kind of a parallel combination is used to increase the current carrying capability. Okay? So instead of making one device with large current carrying capability, you can parallel various devices so that you get effectively a device which has high current carrying capability. Now here, because of the imbalance in the structures of the devices, however much you try to make these devices identical, there will be some imbalance. Because of this, one device will take more current than other devices. Now, since the voltages are the same for all the three devices because they are in parallel, the device which takes more current dissipates more power. It gets heated up, and as it gets heated up, it further increases the current, because you know, in a bipolar transistor the current voltage characteristics of the emitter junction is like a diode. Clearly see that for higher temperature, for any given voltage, the current is more. So here all the three have the same base emitter voltage. So here the current will be more if it is at a higher temperature. This will further increase the power dissipation and further raise the temperature. This is like a thermal runaway, right? It is a situation going out of control, and this device will end up hogging all the current and in the process heated up, and it may also get destroyed. Whereas in the case of MOSFET, no such thing happens. Let us see why. Here, if there is an imbalance between these three devices, and let us say because of that this device takes maximum current, it gets heated up. But since in the MOSFET the current is because of drift, and therefore the MOSFET behaves like a resistor, and you know that the mobility falls with temperature, okay, around the room temperature range where the devices are used. So therefore the resistance increases. Now, which means that if any device gets heated up, because of the increase in resistance as compared to other devices, its current will fall. So this is a negative feedback situation, and because of this the current will get equalized among all the devices. So this is a great advantage in the case of MOSFET, that you can parallel the devices without any second breakdown problem. So in summary, those are the differences between the BJT and the MOSFET. So what we find is that the BJT has the great advantage of very high geometry independent GM, but it has a disadvantages that it is not a bilateral device unlike the MOSFET. Okay? Also, it has a second breakdown problem unlike the MOSFET, which does not have any such problem. So you see there are advantages and disadvantages. That is why both devices are existing today for different applications, though the MOSFET is more suitable than BJT definitely from the integrated circuit point of view. Now with that we come to the end of the discussion on MOSFETs. Let us make a summary of all that we have done in the last few lectures on MOSFET. First we discussed the historical account, how this device has evolved. Then we discussed the device structure and fabrication. Then we considered the DC and small signal characteristics. Here we started with the qualitative analysis, and then we wrote down the equations. And finally we discussed the differences between a MOSFET and a BJT. Now it is emphasized here that our discussion on MOSFETs was parallel to the discussion on BJT. So we considered a certain set of topics for both these devices in a certain order. Now the next lecture will be the last lecture of this course, wherein we will discuss some advanced devices in a very simple manner and also summarize all that we have done in this course.